Good morning. So today's lecture is on momentum and collisions. And so let me set up the lecture slides. So we're going to define a new quantity, momentum, and you're probably wondering why we need to define a new quantity after we've already talked about uh, position, displacement, velocity, acceleration, force, work, kinetic energy, potential energy. Why do we need something else? And the answer is that momentum has a very important property in what are called collisions. And collision, in the physics sense, means any interaction between two objects that where they alter each other's motion or where they influence each other's motion. And that could be the most basic idea of a collision where you have two things hitting each other, but it doesn't actually have to be. As long as they exert some sort of force on each other, then we can say that a collision is in place and what we call the conservation of momentum applies. But let's begin our discussion then. So momentum is the product of an object's mass and velocity. Momentum is a vector. It has magnitude and direction, and it can be broken into components. The definition of momentum, not getting into things like special relativity where the definition gets altered, but the definition of momentum that we use in introductory level physics, we define the momentum vector as P. And again, with the arrow, it has a vector and it's equal to the mass multiplied by the velocity. So it's equal to a scalar multiplied by a vector. So what that means is the momentum has the same direction as the velocity vector, but you're multiplying the velocity by the mass to get the momentum. It's related, it's similar to the relationship between force and acceleration. The force vector and the acceleration vector point in exactly the same direction, and you get force by multiplying the acceleration vector by the mass. So let's go to an example. Calculate the momentum of a 2,000 kilogram elephant charging a hunter at a speed of 7.50 meters per second. So let's go to the whiteboard. So it's a 2,000 kilogram elephant. So the mass is 2,000 kilograms. The velocity is 7.50 meters per second. So the momentum then is equal to the product of mass times velocity. And that's 7.5, just to make that decimal point a little bit clearer. Okay, so you have 2,000 times 7.5, and so that's 15,000. And to three significant figures, you can write that as 1.50 times 10 to the 4. Can make that decimal point a little bit bigger. And momentum doesn't have special units. In SI units, you would just say kilogram meters per second. And so that's the momentum in this case. And that's part A. Part B, so this is question 1 if you're looking at your textbook. Compare the elephant's momentum with the momentum of a 0.0400 kilogram tranquilizer dart fired at a speed of 600 meters per second. So you're setting up a tranquilizer dart. So that's 0.04 0400 kilograms, so 40-gram tranquilizer dart, and you can shoot it at 600 meters per second. And so you do that calculation and you get the momentum is equal to 24.0. It's three significant figures. 24.0. And again, kilogram meters per second. And then the last example, what is the momentum of the 90 kilogram hunter running at 7.40 meters per second after missing the elephant? So the hunter got the elephant angry and is now running for his life. So, and not running as quickly as the elephant. So I'm not sure things are going to end well for the hunter. But P is equal to mv again. And so the mass is 90.0 kilograms. And the velocity is, so this is A, this is B, and this is C. The velocity is 7.40 meters per second. And so that's 90 times 7.4. His momentum is 666. Whoever wrote this problem has an odd sense of humor, meters per second. So these are, basic three examples. Again, momentum is equal to mass times velocity. So let's keep going then. The SI unit of momentum is kilogram meters per second, as you saw in those examples. Momentum can be related to kinetic energy by the following formula. So this comes from the fact that Ke is equal to 1/2 mv squared. So P is equal to mv, so you can write V is equal to P over m, and then substitute that into the kinetic energy equation. And what you wind up getting is Ke is equal to P squared over 2m. So if you know the momentum rather than the velocity, this will save you a step in the calculations if you need to calculate kinetic energy. So what happens when momentum changes? So we're going to define a new vector, the vector of the change of the object's momentum. So this is called the impulse vector. An I with an arrow, so the vector I is equal to delta vector P. So it's also going to be in kilogram meters per second, but it's the change in momentum. So remember how we talk about delta. So that means the momentum at the final time minus the momentum at the initial time. And it's a vector equation. So technically it's three equations, one for each dimension. And the impulse is related to the force. So the impulse is equal to delta P, assuming the mass remains constant. Now, if we talk about rocket propulsion, the mass doesn't remain constant, but in pretty much every other example, the mass does, or in jet propulsion as well. So rocket and jet propulsion, the mass doesn't remain constant. For other situations, if you're talking about two solid objects, colliding or, analyzing the momentum of one solid object, it's going to maintain its mass. So in that case, delta P is equal to m times delta V. From the average acceleration being equal to delta V over delta T, you can also write the impulse as being equal to the mass, m, times the average acceleration times delta T. And of course, the mass times the average acceleration is equal to the average force. So you can write the impulse not just as delta P, but also as the average force times delta T. So sometimes, impulse is the same units of moment as momentum does, kilogram meters per second. But sometimes you'll see impulse described in units of Newton seconds, because the impulse, again, is equal to the average force times delta T. And we can use that to write an equation for the average force, that the average force is equal to delta P over delta T. So the force is equal to the change in the object's momentum over time. So now we're going to move to another example. A bullet is accelerated down the barrel of a gun by hot gases produced in the combustion of gunpowder. What is the average force exerted on a 0.300 kilogram bullet to accelerate it to a speed of 600 meters per second in a time of 2.00 milliseconds? So let's set this up algebraically first, and then we'll go back and get the numbers. So the average force, and there are a couple of ways you can write this that are basically equivalent to each other. But we'll say it's equal to delta P over delta T. And you can write that as the mass being equal to delta V, or the mass times delta V over delta T. And we have all these in this case. So the mass is, and this is problem 7 in the book, the mass is 0.300 kilograms. Zero 0.0300 kilograms, or 30.0 grams. We are told it goes from, you assume the bullet is at rest initially, and it goes to a speed of 600 milliseconds. So delta V, or meters per second, excuse me. So delta V is 600 meters per second. And then the delta T is 2.00 milliseconds. So a millisecond is 1,000th, or 10 to the negative 3. So 2.00 times 10 to the negative 3 seconds. And if everything is in SI units, then your answer is going to be in SI units, which in the case of force means newtons. So it's 0.03 times 600 divided by 2 times 10 to the 3. And that gives 9,000, or to 3 significant figures, 9.00 times 10 to the 3 newtons. So that's the average amount of force that's applied on the bullet as it's going through the barrel of the gun, again, due to the combustion of the gunpowder. And that accelerates the bullet to its final speed of 600 meters per second. So, okay, we've defined what momentum is. We've defined the change of momentum and show that that has a very direct relationship to the force. So what does that mean? Well, again, that's important in the study of collisions. This is why we're introducing this new quantity called momentum. And so any situation where two more objects interact with each other is considered to be a collision. And basically, when they interact with each other, they affect each other's motion. So the most obvious example is when they smack together. But if you're talking about objects that exert gravitational forces on each other, objects that exert electrical or magnetic forces on each other, they don't necessarily have to hit each other to influence each other's motion. And so, a collision applies in physics. The term collision applies in those cases as well. So there are a couple of different types of collisions. The first type is called an elastic collision. And that's when all the kinetic energy is conserved. And typically that happens when the interaction between two surfaces is minimized. Is brought to basically zero. If you reduce the amount of, you get the amount of friction as low as you can possibly go, then you're effectively approximating an elastic collision. So, one example would be billiard balls because the billiard balls are spherical. They make very little surface contact with each other when they alter each other's motion, and um, that makes it possible. Neglecting the friction on the surface of the pool table, that makes it possible to approximate the collision as being elastic. Um, in the lab experiment that you're going to observe later, um, you if you put rubber bands on the sides of the two objects that are facing each other and they collide, you're minimizing the amount of contact. So you don't completely eliminate the friction, but you minimize it. And so you're trying to approximate an elastic collision as best as possible where kinetic energy is conserved. Um, in the real world, you get elastic collisions at the molecular level. The molecules of gas in the air are colliding elastically, for example. But any other type of collision where kinetic energy is not conserved is called an inelastic collision. So basically, every macroscopic level collision is going to be inelastic to some degree. There's almost always going to be friction somewhere, especially if the two objects are in contact with each other. And so you need to take into account how much kinetic energy is lost. The most kinetic energy that you can lose in a collision is the perfectly inelastic collision, where not only do the surfaces collide with each other, they stick together. And then the two objects move together as one from that point. So that's a perfectly inelastic collision. And it's the most possible energy that you can lose. Now, here's the key with momentum, and this is why momentum is such an important thing to study and to understand. So let's start with the collision between an object of mass m1 and initial velocity vi1 and an object of mass m2 and initial velocity vi2. From Newton's third law, every action has an equal and opposite reaction. The objects exert an equal and opposite force on each other. So the net force on the system, treating the two objects as the system, the net force on the system is zero. They exert equal and opposite forces on each other. So you add those force vectors together, you get zero. So the net force acting on the system, and again, this is assuming you've eliminated friction, you're on a level surface, so gravity doesn't come into play. So it's kind of idealized, but the basic idea applies. The objects exert an equal and opposite force on each other so that the net force on the system is zero. But let's go back a couple of slides to force average is equal to delta P over delta T. If the force, this equation applies to individual objects, this equation applies equally well to systems of objects. So if the net force acting on the system of objects is zero, then the change in the momentum of the system of objects is zero, which means that momentum is conserved. So again, assuming neither object is deformed in the collision, the net change in the momentum is zero, which means the total momentum in the system before the collision equals the total momentum of the system after the collision. And so so basically collisions that do not involve any deformation, a change in the shape of the objects, obey the principle of conservation of momentum. And so mathematically, you can explain it like this: m1 v1i plus m2 v2i. So the initial momentum of the first object plus the momentum of the second object equals the final momentum of the first object plus the final momentum of the second object. And obviously, you can extend that for, if there are multiple objects involved in the collision, you can extend that for as many objects as there are. With one important qualification: since momentum is a vector, Equations can be needed for both the x and y directions. So if there are two dimensions involved in the collision, um, this becomes this becomes two sets of equations. So momentum in the x direction is conserved and momentum in the y direction is conserved. And if necessary, if you need to go to all three dimensions, momentum in the z direction is conserved as well. And keep in mind the components of the velocities and therefore the components of the momentum vectors can be positive or negative. So let's say you have one object moving to the right initially and one object moving to the left initially. And you define the positive as to the right. So the object moving to the right has a positive initial velocity, which means it has a positive initial momentum. The object that's moving to the left has a negative initial velocity and a negative initial momentum. And you need to take those positives and negatives into consideration when you're evaluating the momentum before the collision and then setting it equal to the momentum after the collision. So that's very important. And, this is something that keeps coming up in physics. Always keep track of your positives and negatives, especially if there are multiple dimensions involved. So let's go to an example. This is number 23 in the book. Professional application. Train cars are coupled together by being bumped into one another. So basically, you push one into the other and then they link together. And so when they stick together, that's a perfectly inelastic collision. Suppose two loaded train cars are moving towards each other, the first having a mass of 150,000 kilograms and a velocity of 0.3 meters, 0 meters per second, and the second having a mass of 110,000 kilograms and a velocity of negative 0.120 meters per second. The minus indicates direction of motion. So again, keeping track of positives and negatives. So we'll say the first one's moving to the right and the second one is moving to the left. What is their final velocity? So to start with, we'll go to the whiteboard and we will visualize this. So you have your train, and I'm not going to draw the wheels in the train. So you have M1 moving to the right at VI1, and M2 moving to the left at we'll call that VI2. Let me just be consistent with this. That's all right. So V1I, and we'll make this V2I. All right. Okay, so they're going to collide, and we're told they're going to collide inelastically, which means, or perfectly inelastically. So they link together. So M1 V1I plus M2 V2I is equal to, from momentum conservation, M1 plus M2 VF. So the total momentum before the collision is equal to the total momentum after. And since V2 or M2 is moving to the left, its initial velocity is negative. So we want to solve this for VF. And so we'll do that algebraically first and then go back and plug in the numbers. So VF is equal to M1 V1I plus M2 V2I. And you're dividing that by M1 plus M2. And so we have M1 as being 150,000 kilograms. V1I is 0.300 meters per second. So that's the momentum of the first train car. And then plus the second has a mass of 110,000 kilograms, so it's a little bit lighter. And it's moving at negative 0.120. All right, let me make this a little bit smaller so we can fit it. And you're dividing that by 260,000 kilograms. So the total mass, M1 plus M2. And so then you plug everything in. So the second mass is lighter and it's also moving more slowly. So its magnitude momentum is less than the first one. So you would expect the total momentum to wind up or in the positive direction. And so that's basically what you're doing in the numerator, the total momentum. So that's 150,000 times 0.3 plus 110,000 times negative 0.120. And so you get 31,800 kilogram meters per second. It's positive, so that when they link together, the two of them are going to move to the right. And you're dividing that by 260,000 kilograms. And so you get a final velocity of zero, and it's positive, 0.122 meters per second. So it's when they link together, they are going to move to the right at a speed of 0.122 meters per second. So the first cart has slowed down significantly. The second cart has had its direction reversed by the collision. And that can happen. And so it also is actually it hasn't slowed down, if you'll notice. It's actually increased its speed, but its direction has reversed. So you get the final velocity. And again, because they link together, there was only one unknown in this problem. So let's get back to the slides. Another example, this is number 24 in the book. Suppose a clay model of a koala bear has a mass of 0.20 kilograms and slides on ice at a speed of 0.50 meters per second. It runs into another clay model, which is initially motionless and has a mass of 0.350 kilograms. Both being soft clay, they naturally stick together. What is their final velocity? So the ice is basically, is a way of saying neglecting friction. It won't necessarily be zero, but if the collision is more or less instantaneous, friction won't have enough time to significantly affect the result. So if you're looking immediately before the collision and immediately after the collision, friction won't have enough time to significantly affect the results. And that's basically what this is saying. And that's what makes the air track experiment work, that you're going to observe in the lab. That you've minimized friction enough so that it's not going to slow things down between the moment before the collision and the moment after the collision. So, and it's, again, another perfectly inelastic collision. They stick together. So there is only one unknown, their final velocity. So let's get back to the whiteboard. Now, conveniently, we can use most of what we've already set up. So what I'm just going to do is erase the last part. And we could even use this diagram to some degree. But the second one is initially motionless. So there's no motion here. So it looks like this initially, that M1 is coming towards M2. They stick together. So V2I is equal to 0. And then they continue forward. So we can erase this term and we can erase this term. So the initial momentum in the system is solely from the first object or the first clay bear. And then once the collision happens, the final velocity is, or the final momentum is equal to the initial momentum. It's also equal to the total mass multiplied by the final velocity. So again, there's only one unknown. And so you can use this equation here. You don't need the V2y because, again, the second clay bear is motionless. So now we can plug things in. So the mass of the first clay bear is 0.200 kilograms and 0.750 meters per second. So that's the initial momentum of the system. And you're dividing it by the total mass to get the final velocity of the system. So the second clay bear has a mass of 0.350 kilograms. So the total mass is 0.550 kilograms. So the sum of the two. And so you take the initial momentum, which is also equal to the final momentum, divided by the total mass, and that gives you the final velocity when the two are sticking together. So 0.2 divided by 0.3. And what you get is 0.273 meters per second as the final velocity. So the first one slows down considerably. The second one gets a push forward and starts moving, but they're moving together because it's a perfectly inelastic collision. And because it's a perfectly inelastic collision, the equation only requires one unknown. And so we're going to do a third example. A 2.40 kilogram billiard ball that is moving at 3.00 meters per second strikes the bumper of a pool table and bounces straight back at 2.40 meters per second, so 80% of its original speed. The collision lasts 0.0150 seconds. Calculate the average force exerted on the ball by the bumper. And just to understand what happens here, the ball exerts the same force on the bumper. Momentum is not conserved in this case because there are other forces involved. There are other forces on the pool table holding the bumper in place so that it doesn't move. Again, that's important that the conservation of momentum applies when there are no other external forces involved, just the forces between the two objects. But in this case, that's not the case. So we're asked to calculate the average force exerted on the ball by the bumper. So the average force is equal to, and it's a one-dimensional problem, so I won't bother with the vector signs. So it's delta P over delta T, and we can write that as M times delta V over delta T, which we can write as M, its final velocity is 2.40 meters per second. So VF minus VI divided by delta T. So the mass of the pool ball is 0.240 kilograms. Now, the final velocity is 2.40 meters per second. And we'll define that as the positive direction. And then we're subtracting from that the initial velocity, which is 3.00 meters per second, but it's in the opposite direction. The pool ball shifts directions. So we'll define its initial velocity as being negative 3.00 meters per second. And that's kind of important. Again, keep track of positives and negatives. So if you define positive as the direction the ball is moving after the collision, then before the collision, it's moving with a negative velocity. And all that is divided by delta t. And so delta t is 0.150 seconds, or 15.0 milliseconds if you prefer. So that's 2.4 minus negative 3, which is equivalent to 2.4 plus 3. So that's 5.4 times 0.24 kilograms divided by 0.0150 seconds. And that gives an average force of 86.4 newtons. Okay, so you have an average force, and again, it's equal to the change in momentum divided by the change in time. So that's another example of the collision, and it's an inelastic collision. Kinetic energy was not conserved. It's not a perfectly inelastic collision because the ball and the bumper do not stick together. Okay, so two more examples before we get to elastic collisions, which are a bit more complicated than perfectly inelastic collisions. So here, this is number 44 in the book. During an ice skating performance, let me get out of this so we can get to the new example. During an ice skating performance, an initially motionless 80.0 kilogram clown throws a fake barbell away. The clown's ice skates allow her to recoil frictionlessly. In real life, it's approximately frictionlessly. So what exactly does that mean? Well, this is an example of a collision in reverse. That the total initial momentum is 0. The clown is not moving. The barbell is not moving. But the clown throws an object, but the clown is standing on frictionless ice. So the clown exerts a force on the object exerts a force back on the clown. And if there's nothing like friction or any other force holding the clown in place, the clown will move backwards. And again, that's Newton's third law. And one of the consequences of Newton's third law is that the total momentum in the collision or in this interaction is conserved because there's no external force involved. So if the total initial momentum of the system is 0, the total final momentum of the system is also 0. And so the first thing we're asked is, if the clown recoils with a velocity of 0.500 meters per second, and the barbell is thrown with a velocity of 10.0 meters per second, what is the mass of the barbell?
I'm on it.
Siri. All right. So let's get to the, just illustrate this. So you have the clown. I won't draw details. And icy surface. The clown is on skates. And so you have some sort of barbell. And so we'll call that, let's see, it's moving, we'll call its velocity VB for the velocity of the barbell. The clown is then going to be pushed to the left. We'll call that VC. And so the total initial momentum of the system is 0. And then that's equal to the final momentum of the system, which we'll call MCVC plus MBVB. We'll define the positive direction as to the right, which is the barbell's direction. So we are asked to find the mass of the barbell given all this and the other information. So you solve this for MB. So you bring this term to the other side by subtracting it. and that equals mb vb. And we want to solve for the mass of the barbell, so we divide both sides by the velocity of the barbell. So that's negative mc vc divided by vb. So now we plug in terms. So we have negative, and again, keep track of positives and negatives. The mass of the clown is 80.0 kilograms. The velocity of the clown, now remember, we're defining forward, or the positive direction, as the velocity of the barbell. So the velocity of the clown is negative 0.500 meters per second. So the negatives will cancel each other out. The velocity of the barbell, which is going in the forward or the positive direction, is 10.0 meters per second. And so what you get out of that is that the barbell, again, the negatives cancel out, has a mass of 4.00 kilograms. So their momentum vectors will be equal in magnitude and opposite in direction. Again, because the initial momentum of the system is zero. They're not moving initially. They're not moving until the clown throws something. And maybe you've observed something like this. It would typically have to be a low friction surface. So let's say you're on a sled and you throw a snowball. Your sled will move in the opposite direction that you threw the snowball. And so maybe you've observed something like that at some point in your life. But that's basically what happens, is that the total momentum initially was zero, and the total momentum remains zero. But if you've given something a forward momentum, that object has given you a backwards momentum, an equal magnitude but backwards momentum. And so that's that's something you can try at home, at least when there's snow or ice. I recommend being careful if you do try it at home. But but that's something you can actually observe. Okay, one more example before we get to elastic collisions. And this is number 32 in your book. During an ice show, a 60.0 kilogram skater leaps into the air and is caught by an initially stationary 75.0 kilogram skater. What is their final velocity, assuming negligible friction, and that the 60.0 kilogram skater original horizontal velocity is 4.00 meters per second? And then you're asked how much kinetic energy is lost. So again, a perfectly inelastic collision. When one skater catches the other skater, that's equivalent to them sticking together. They move together in unison at that point. So that falls under the banner of a perfectly inelastic collision. So again, there's only one unknown, the final velocity. And so how much kinetic energy is lost? So there's a little bit of additional to this problem. So let's get back to the whiteboard. So we've already set up this equation. And so m1 v1I is equal to m1 plus m2 v2 or v final. Again, perfectly inelastic collision. And the second skater is at rest. So the second skater does not have any initial momentum. So you then solve this for VF. And so that's equal to m1 v1I divided by the total. And so the 60 kilogram skater is moving initially at 4.00 meters per second. about 9 miles per hour. And you're dividing by the total mass. So one is 60.0 kilograms, the other is 75.0 kilograms. So you add those together, you get 135.0 kilograms. You actually gain a significant figure, but since you're dividing, since the two numbers in the numerator still only have 3, it's not going to affect the end result. So that's 60 times 4 divided by 135. And so that's 1.78 meters per second. But now there's a little bit of a catch to this problem. We're asked to do a little bit more. We're asked to find out how much kinetic energy is lost. So let's figure out the initial kinetic energy. That's equal to 1/2 m1 v1I squared. And so that's 1/2 times 60.0 kilograms times 4.00 meters per second. And don't forget you're squaring it. And so that gives the initial kinetic energy of the system. 0.5 times 60. And so that gives 480 joules. So that's the initial kinetic energy of the system. And in a perfectly inelastic collision, the most possible energy that you can lose while still conserving momentum has been lost. So, and yes, it's possible for in a perfectly inelastic collision to wind up where they stick together and then stop. So to wind up with 0 kinetic energy. If the net initial momentum was 0, that will happen. So the final kinetic energy is 1/2 m1 plus m2 times v final, which we just figured out, squared. So that's 1/2 135.0 kilograms multiplied by 1.78 meters per second. And don't forget you're squaring that. And so you get 214 joules. So the change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy, which is equal to negative 266 joules. So it loses 266, the skaters lose 266 joules of kinetic energy. And that gets lost as heat, as friction in the inelastic collision, or in this case, the perfectly inelastic collision. And so more than half of the kinetic energy has been lost that way. Okay. Now we're going to move on to elastic collisions. So we're not going to go into the derivation, although the textbook follows the steps. It's a bit lengthy, so I'm not going to do that derivation. But you can, in elastic collisions, you typically have 2 equations with 2 unknowns. Remember, with perfectly inelastic collisions, you typically only have 1 unknown. In elastic collisions, you typically have 2 unknowns, but you get 2 equations because momentum is conserved and because kinetic energy is conserved. And so the equation for kinetic energy conservation, if momentum is also conserved, can be simplified. So you can write that as V1I minus V2I equals V2F minus V1F. You can also write that as V1I plus V1F is equal to V2I plus V2F. But that equation is true if kinetic energy is conserved. And so it's a simpler version. It makes doing the algebra simpler. And so now you have two equations with two unknowns. And we're going to finish with showing one example of that. And so this is number 28 in your book. Two identical objects, such as billiard balls, have a one-dimensional collision in which one is initially motionless. After the collision, the moving object is stationary and the other moves with the same speed as the other originally had. Show that both momentum and kinetic energy are conserved. So basically, you have a pool ball with mass m. And so this is before. And so it hits another pool ball with mass m. So this will be m. We'll call it m1 and m2, but we know that m1 and m2 are equal to each other. And so this is v1i. And then after, we are told that m1 stays in place. And that v2, the second pool ball then goes off at the velocity v2f. And we are given that they're identical, so that m1 is equal to m2. And we are also given, looking back at the problem, that the other moves with the same speed as the other originally have. Well, that's a bit complicated. Basically, m2 moves with the same speed that m1 initially have. So v2f is equal to v1i. And this is something you'll observe in the lab experiment, that when the two carts have identical mass and you hold one of them motionless in the middle, when you launch the first cart towards it and they collide, the second one will go off at essentially the same speed. The first one will stop in place. And that's what you should expect to observe in an at least approximately elastic collision where the masses involved are equal. But now we're going to demonstrate that momentum and kinetic energy are both conserved in this collision. So we'll start with momentum. So P initial is equal to m1 v1i. P final is equal to m2 v2f. But we've already been told that these are identical pool balls. So m2 is equal to m1. And we've also been told that v2f is equal to v1i. So momentum is definitely conserved in this case. But what about kinetic energy? Well, the initial kinetic energy is equal to 1/2 m1 v1i squared. And the final kinetic energy is equal to 1/2 m2 v2i or v2f squared. But we already know that these are going to, m2 is equal to m1 and v2f is equal to v1i. So again, kinetic energy is indeed conserved in this type of collision. So basically, we're showing that this is an example of an elastic collision. And like I said, in the lab experiment, you will be able to observe that. So with that, we're going to close up today. We're going to be doing on Tuesday some more involved problems, especially where elastic collisions are conserved. But that's momentum in a nutshell. Again, the lab is going to start at the regular time, which is 12:35, or rather 12:30. And Professor Schnall will be hosting it. So good luck with everything. Have a good weekend. I will see you on Tuesday.